So in this video, we're going to look at getting combinations with repetition. We've already looked at permutations where we did things like permuted the letters in ball, and we had the two L's, so they were repeated. Combinations are a little bit harder because we already don't care about order in a combination. And so let's dive right in with an example. Three friends go into a diner. At the diner, they can order either pizza, falafel, or a burger. If an order is unique based solely on the quantity of each item ordered and not on who orders what item, then how many different orders can be made? And I'm going to assume for this problem that all three are ordering something, one thing. And so you might think, okay, how can I go after this? And simplest starting point, not easiest way to get the answer at the end of it all, is to just try to come up with a list. So I'll just make a little table to help organize my thinking. So we have either pizza, falafel, or burger. And if they're each ordering one thing, I need a total of three things. So I could have one person order a pizza, one person order a falafel, one person order a burger. And notice, I don't care who orders what. If I had that, if I did care, that'd just be 3 to the third power, because 3 choices for friend 1, 3 choices for friend 2, 3 choices for friend 3. But it doesn't matter if this is the first person, second person, third person, or if this is the third person, first person, second person. It's the same order from the viewpoint of the diner. What do you say? I want one of these, one of these, one of these. So they can each have one. Or we could have two people order pizza, one order falafel, no burgers. 2 order pizza, no falafel, 1 burger. 1 order pizza, 2 falafel, no burger. 1 order pizza, no falafel, 2 burgers. Or I could have no pizza, 2 falafel, 1 burger. No pizza, 1 falafel, 2 burgers. So now these are all the cases where 2 people order one thing, 1 person orders a second, and no one orders the third. And then the final case, what if all 3 people order the same thing? Well, there can either be 3 pizzas, no falafel, no burger, no pizzas, 3 falafel, no burgers, and no pizzas, no falafel, but 3 burgers. And so if we had no better way to get after this problem, we can see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible orders. But there's got to be a better way, and there is. So what we can do is consider it this way. We have 3 friends that are, for this problem, interchangeable. So I can just mark them off as, little dots, circles, whatever. 1 dot is the same as another dot. 1 friend is the same as another friend for this. And I need to split them into 3 groups. And basically, that means that I'm going to have to put in dividers. So I'll just put these as like dividers. And what this means is I only need 2 dividers because 2 dividers will split us into 3 groups. This 1 and 1 and 1 would look like 1 in the first group, divider, 1 in the second group, divider, 1 in the third group. This 2 and 1 and 0 would be 2, then a divider, then 1, then a divider, and nothing over here in the third group. And you can see, so I'll put a little ellipsis, down here, 3 and 0 just means I have all 3 out front, the divider, nothing in the second group, divider, nothing in the third group. Or in this case, divider, 3. And what you can see here is the number of possible ways to make this order is going to be equal to, in this case, 5, choose 3. Or you could also think of this as 5 factorial for permuting these 5 elements, divided by 3 factorial for these 3 being identical, and 2 factorial for these 2 being identical. And this leads straight into a formula we can use. So the formula for combinations with repetition. And in here, so the number of ways to choose R objects from n distinct objects with repetition allowed. Is going to be, we have n distinct groups. This right here is the number of groups. And then this is the identical element. So if you remember, when we had groups in the last one, if there are n groups, that means we need n minus 1 dividers. And that leads us to the formula. So we should have R plus n minus 1. So R plus n minus 1 total objects to permute the R objects. These would be the 3 friends from the previous example. And then the n minus 1 dividers, the 2 dividers from the last example, to get us the 3 distinct groups. And then I can divide that by R factorial, because each of the R objects is in that permutation, times n minus 1 factorial. And the sort of final form of the formula that you'll see in many books is just going to be this. Instead of writing out all the factorials, they will write it as n plus R minus 1, choose R. N being the groups, R being the things we're putting into those groups, and that R being the things we're putting into those groups. This minus 1 because we only need one fewer divider for there. So from our example, we were choosing R objects. So we had R people, 3 people, the friends, choosing one of 3 distinct objects. So n equals 3 for the pizza, falafel, burger. And then this all gets us to the formula, 3 plus 3 minus 1, choose 3, which is 5, choose 3, which is, and I'll just go up here, I apologize for the sort of circuitous route around this page, 5 times 4 times up with the 3 factorial, which is going to cancel out with the 3 factorial over here, and I'm going to have a 5 minus 3, 2 factorial. Those cancel. 5 times 4 divided by 2 gives me 10. Same we had on the previous one, except this I can sort of just put in the calculator. Alright, let's look at another example. Make sure we've got this idea. So, I have 10 cookies. I want to split them in some way between 4 children. And how many ways can I split these 10 cookies between the children? And how many ways can you split these cookies for part B so that each child gets at least 1 cookie? So in this case, the n is the number of children. Each child is different. Giving all cookies to the first child is a different case than giving all the cookies to the second child or the third child, or and then any other thing. So the R, we're choosing basically 10 times we're choosing the different children. So what happens is we sort of have these 10 cookies, and we're going to split it into 4 groups. So I need these 3 dividers that will then go somewhere in here. And so that gives me n plus r, so 4 plus 10 minus 1, choose 10, which is going to be 13, choose 10. 13 factorial over 13 minus 10, 3 factorial, 10 factorial. 13 is 3 bigger than 10, so I have 13, 12, 11. The 10 factorial is going to cancel. 3 times 2 times 1. And I work this all the way out. Let me see what I get. I should end up with 286 possible ways to give these cookies to the children. For part B, it's almost the same. Here's the trick. If I want to make sure that each child gets at least 1 cookie, all I'm going to do is take the 10 cookies, give 1 to each child, and I'll have 6 cookies left to distribute amongst the children. And that way, like, if of these 6 cookies, I give 0 of these cookies to child 1, child 1 already has 1 of the 4 cookies I took out at the beginning, so that child still has at least 1 cookie. And same thing, this is R, this is still N, and I would just do, let's see, 4 plus 6 minus 1, choose 6, which is going to give me 4 plus 6 is 10 minus 1, 9 factorial over 9 minus 6, 3 factorial, 6 factorial. The 9 and the 6, 9 is 3 more than 6. I'll write it out. I didn't write it out here all the way, but I'll write it out. Again, feel free to skip that. So 9 factorial is 9 times 8 times 7 times 6 factorial, which is going to very quickly cancel with this 6 factorial. And now 9 times 8 times 7 divided by 3 times 2 times 1. Well, 9 over 3 is 3. 8 over 2 is 4. So I get 3 times 4 times 7, which of course gives me 84 possible ways to split up these cookies so that each child gets at least 1. Okay, next video up will just be some practice problems getting through these combinations with repetition.